In this lecture, we'll learn about a few new functional groups. And the reason we'll cover these functional groups now is that each one has its own similarities to the alcohol functional group. The first functional group we'll discuss is the ether functional group. Ethers have a general form that is structurally similar to alcohols. Here's why. Like alcohols, ethers are based around an oxygen atom, and specifically an oxygen atom that has two single bonds. In an alcohol, we'd expect these single bonds to go to a carbon chain on one side and a hydrogen atom on the other. In ethers, the oxygen is bonded to a carbon chain on one side, but rather than having a hydrogen on the second bond, we replace the hydrogen with another carbon chain. So an ether is essentially an oxygen atom sandwiched between two carbon chains. For that reason, the shorthand for ether looks like this, ROR. Ethers can be classified in two general categories, symmetrical ethers and unsymmetrical ethers. As you would guess, it has to do with whether we have a mirror image in the molecule. To be even more specific, it depends on whether the R groups are identical or different. For example, if we consider the R carbon chain on the left side to be R1 and the R carbon chain on the right side to be R2, then a symmetrical ether is one in which R1 is the same as R2. Maybe they're both methyls or ethyl groups. In an unsymmetrical ether, R1 would be different than R2. So maybe we have an ethyl and an isopropyl. Ethers are also related to another structure called epoxides. And we won't cover these in any detail, but I want to mention it because many people have already heard the word epoxide. What an epoxide actually is simply an ether that has one extra bond connecting the carbon on the left side to the carbon on the right. And in fact, if you're familiar with epoxides, you know that they're typically used as glues or coatings that are very, very hard. The way that they're mixed together is to combine an ether with another chemical compound that will help that third bond form. Hence, we get this triangle-shaped structure and typically a very hard substance. But back to ethers. Physically, ethers act much the way that we've seen all organic molecules act. Depending on how many carbons they have, their physical properties can vary. They are polar molecules because of the oxygen, but if those R groups are very long carbon chains, we may not see that manifest itself in terms of things like solubility. It's worth pointing out that while ethers are polar, one ether cannot hydrogen bond with another ether, because while they have oxygen, they don't have hydrogen directly connected to that oxygen. This isn't true, however, if you mix an ether with another molecule, such as water. In that case, the water can provide the hydrogen for a hydrogen bond, while the oxygen in the ether can actually act as the other side or the other part of the hydrogen bonding interaction. As a result, ethers are sometimes more soluble than you might expect of a polar molecule in other hydrogen bonding solvents. Naming ethers is very easy because many people simply refer to them by their common names, and we're going to do the exact same thing. So let me show you how to name an ether using common non-IUPAC naming. It's really easy because all we have to do is name each alkyl branch, then arrange the names alphabetically and classify it by saying the word ether. I'll show you an example. In this molecule, which is an example of an ether, I have two different R groups. So specifically, this is a non-symmetric or unsymmetrical ether. On the left side of the molecule, I have an ethyl group because it contains two carbons. On the right side, I have a methyl group. And as we already said, it's an ether molecule. So in order to name this molecule, I put together the names of the alkyl branches alphabetically and I add the word ether. Hence, the name of this molecule, at least in common terms, would be ethyl methyl ether. As you can imagine, a lot of these get to be kind of fun to say. Try naming this ether. As we look at this molecule, we see that on the left side, I have a propyl group. And it's just a boring old propyl group. It's not isopropyl or anything special. On the other side of the molecule, I also have a propyl group. So while you could call this propyl-propyl ether, you might have guessed that a much more convenient thing to call it is dipropyl ether. Again, it's not IUPAC naming, so we usually just do what sounds right. There is a way to name these using IUPAC nomenclature, and it involves what's called alkoxy naming. For instance, when it comes to the molecule on the left side of the screen, the IUPAC name of that molecule would be methoxyethane. We're not going to cover IUPAC naming of ethers in Chem 122, somewhat to save time, but mostly because people are very comfortable just hearing ethers referred to by their common names. In addition to their role in epoxides, ethers actually have a really interesting history in medicine, and that's because historically, ethers were some of the first substances that were used as inhaled anesthetics. An anesthetic is a substance that someone takes in order to relieve pain, and ethers have been used in this way for more than 150 years. However, they're predated by a lot of other substances that human beings have used to relieve pain, and I actually want to take a couple minutes to talk about the history of ethers as anesthetics. In order to do this, let me just give you a little bit of background, and I'm going to require a very technical timeline to do this. So there we go. On the left side of the screen are old times, and on the right side of the screen are modern times. Now, for hundreds and thousands of years, human beings have been aware that they want to relieve their pain. And some of the earliest ways that they did this was by ingesting opiates or alcohol. Opiates come from plants like the poppy flower, and in fact we still use opiates because things like codeine and morphine are opiates that we can synthesize in the lab. We know that opiates have been used for thousands of years. In fact, in the famous Greek mythology book, Homer's Odyssey, there's references to opiate use. Even older than opiates are alcohol, or drinking ethanol. You may be aware that when people are under the influence of an alcoholic drink, sometimes they're not aware of the fact that they're experiencing pain. And this has been made quite famous by scenes from events like the Civil War, where people needed to have a leg amputated and they were often given a shot of alcohol just before the procedure. That was meant to be done as an anesthetic, although not a very effective one. Now, the history of modern anesthesia probably starts in about the mid-1800s, and I want to start by telling you about a man named Horace Wells. Horace Wells was a dentist, and based on some of the historical records we have, he was a very caring, empathetic person. So as a dentist in the mid-1800s, a lot of what you did was removing teeth, and you had to do that without the benefit of modern anesthetics. So while Horace Wells could offer a patient a shot of whiskey, after that, you basically just had to tear the tooth out. And not only is this painful for the patient, it really bothered Horace Wells. Then, in the early 1840s, Horace Wells was out for an evening of entertainment. And he did what was very fashionable to do back then, which is to attend a demonstration of laughing gas. Laughing gas is nitrous oxide, and one of the very coolest things that you could do for some entertainment was go to a place where you were allowed to inhale it, or just watch other people inhale it. So if you look, this is a classic example of an advertisement. Nitrous oxide, or exhilarating laughing gas, 30 gallons of gas will be prepared and administered to all in the audience who desire to inhale it. And my absolute favorite part of this is this part down here. The gas will be administered only to gentlemen of the first respectability. The object is to make the entertainment in every respect a genteel affair. So you went to a place, you did some drugs, you watched everybody act like idiots, but it was a genteel affair. Okay. Well, Horace Wells went to see this laughing gas being administered, and he watched a gentleman inhale the gas and start running around the tent, acting like an idiot. But in that process, the gentleman was running into objects, and he ran into them so hard that at one point he actually injured his leg quite badly. But he didn't notice. He just kept running around and eventually returned to the stage. As a dentist, Horace Wells instantly saw the potential for this use of laughing gas, or nitrous oxide, during a dental procedure. So Horace Wells went home and he decided he would try administering laughing gas to himself. Now, we don't know whether he put the gas into a sheep's bladder or a sheep's stomach, but we know that then he used a wooden stick to inhale the gas, and he allowed one of his partners to remove a tooth. And it worked. He didn't feel any pain. So then he started trying it on his patients, and they all reported that they didn't feel any pain. So he was ready to go public with this discovery. So in 1845, he takes his laughing gas and he books the operating theater at Massachusetts General Hospital. Now, an operating theater is what it sounds like. It's basically an auditorium with a surgeon's table at the front. And Horace Wells asked one of his patients to come and have a small procedure done. Now, we don't know exactly what went wrong, but basically the patient did not inhale enough of the gas. So reports differ. Some people say that the whole procedure went through, but then the patient was still in quite a lot of pain. Other reports have the patient jumping up, screaming bloody murder, and running from the room. In either case, Horace Wells was just humiliated. In fact, some people say that people in the room started shouting, "Humbug! Humbug!" because apparently that was the worst thing you could shout at somebody in 1845. So Horace Wells leaves the room humiliated and goes back to his office to consider what to do next. Now, there was another man in the audience that day, and his name was William Morton. He was another dentist, and he was actually a friend of Horace Wells. He was a little horrified by what happened to his friend, but he thought the idea here was good, that you could inhale a substance that would essentially knock you out. And he had been attending a series of chemistry lectures and had just been introduced to the substance ether. So he goes back to his dental practice and starts practicing on patients using ether, and it seems to be working. So he does exactly what Horace Wells does. 1 year later, in 1846, William Morton books Massachusetts General Hospital's operating theater, the exact same room as Horace Wells. He invites in a patient who needs a small tumor removed from their jaw, and he proceeds to put the patient under the influence of ether and extract the tumor. When the patient comes to, William Morton asks the patient, "Did you feel any pain?" And the patient says, "I felt no pain." At this point, William Morton turns to the audience and says the famous line, "Gentlemen, this is no humbug." And the rest is history. If you want a good vacation adventure, Massachusetts General Hospital's famous operating theater still exists, and in fact, because of this story, it's actually referred to as the Ether Dome, and to this day you can go sit in it and see where this happened. This story does have a really sad and actually quite disturbing ending. Horace Wells, humiliated from the failure of his nitrous oxide, starts roaming around the country and eventually ends up in Europe trying to find another substance that might work better so he can reclaim his name and continue to help his patients. He ends up settling on the substance that we know as chloroform. And just like he did with the nitrous oxide, he tries experimenting with it on himself first. He becomes addicted to the chloroform, and eventually he ends up back in the United States. He's in his lab, he takes the chloroform, and he suffers a total break with reality. In the next horrifying minutes, he grabs a container of sulfuric acid nearby, runs down the stairs onto the street below, and flings the sulfuric acid onto the first group of women that he sees. He's gone completely insane. The women are horribly disfigured. He's arrested, he's put on trial and found to be insane and put in a mental institution where he commits suicide when he realizes what he's done. So it's a tragic end for Horace Wells. It's also a sad piece of history because the fact is, in our modern era, we recognize that nitrous oxide is far superior for use during dental procedures than ether. And believe it or not, even though William Morton gets all the credit for ether and the Ether Dome in 1846, now when we look back with all of our modern knowledge, we find that there were people using ether well before him. In fact, famously, a dentist in the South named Crawford Long had been using it in his practice since 1842. So there's a couple lessons here. 1, ether has an interesting history. 2, publish your research because it can benefit other people. And 3, don't experiment on yourself with new drugs. It never turns out well. Now, ether has not completely disappeared, as we'll talk about in a minute. In fact, most of the modern inhaled anesthetics that we use in surgery today are halogenated ethers, and we'll talk about what exactly a halogenated compound looks like in a minute. So when we talk about ether as an inhaled anesthetic, we're actually talking about one specific compound, diethyl ether. That's what William Morton used on that famous day in 1846. And it continued to be widely used from then through about the 1940s in the United States, and it's actually still used around the world in certain settings. The reason people like ether as an anesthetic is that it works very, very quickly, it's very efficient, and it's very inexpensive. So it's easy to make, it's easy to administer to a patient, and it works well. There's two major downsides to ether, which explain why it's not used widely in the United States anymore. The first is the patients experience terrible nausea after being administered ether. I've been able to talk to a couple people that have had ether administered in other countries during surgical procedures, and they describe it as being like the worst hangover in history. For those of you that haven't had a hangover, good for you. Think of it like a really bad stomach flu times 10. That's, first of all, unpleasant, and second of all, that's dangerous if you've just had a surgery that's left you very fragile. We don't need anybody going through heaving and vomiting when they might have sutures that could rupture. So that's one downside to it. The other downside to it is that it is a flammable gas. So as an inhaled gas, it spreads around the room if it's not carefully controlled. And because it's flammable, it can ignite very quickly, and that's a huge problem in modern operating theaters. Think about all the cauterizing agents we use, all the electronics that could spark. All of those could create a huge problem with ether. So for that reason, we really don't use it much anymore. Now, I mentioned that many of our modern anesthetics are actually halogenated ethers, and that puts them in a broader class of compounds called halogen-containing compounds. You guys already know perfectly well that halogens are the elements in group 7. We often run into them on compounds, and when we do, we name them using a very simple IUPAC naming rule. We use prefixes depending on which element is in question. So if you're using fluorine attached to an organic molecule, we use the prefix fluoro. If you're using chlorine, we use the prefix chloro. For bromine, it's bromo, and for iodine, it's iodo. So let's do an example. Let's say we have a simple alkane, like pentane. Now, if I attach a chlorine to that pentane, here's how I'll name it. I know it's a pentane, and I know there's a chlorine attached to it. Just like we've done with most of our other organic structures, I'll number the backbone so I can identify where the attachment took place. Because it's on the second carbon, I would call this 2-chloropentane. Pretty straightforward. Generally, these halogens don't take a lot of priority when naming. So if you're naming an alkene or an alcohol, focus on getting those functional groups to the smallest number before you worry about where the halogen will fall in your numbering system. Now we're going to talk more about these halogen-containing compounds. The thing about halogenated compounds is that they are absolutely ubiquitous. Ubiquitous is a word that means everywhere. Basically, you can't escape them. If you're working with any substance, there's a good chance there's a halogen in it. Two places that they're especially pervasive are in pharmaceuticals and in substances called perfluorocarbons. Now, we've seen a lot of examples of pharmaceuticals already in this class, and we'll see many more later on, but I want to focus on perfluorocarbons just for a minute. Perfluorocarbons are just organic structures in which all of the hydrogens have been replaced with fluorine atoms. So whether it's a relatively simple structure or whether it's a longer, more complex structure like a polymer, if we take everywhere where a hydrogen might have been present and replace it with a fluorine, we've created what is generally referred to as a perfluorocarbon. Here's why this is interesting. We know already that carbons and hydrogens on a hydrocarbon molecule give us a nonpolar molecule. Well, fluorine is the most electronegative element on the periodic table. So what that means is on a perfluorocarbon, all of the electrons are being pulled towards the fluorines. Because the fluorines are in every available position, in this case, they're the only thing that's present instead of carbon, that means the electrons basically get pulled towards the sides and the outer limits of the molecule, and they get held there very strongly. The consequence is that you create a molecule that's not just nonpolar, it's beyond nonpolar. It's like a nonpolar molecule where you even eliminate those temporary electron movements that cause London dispersion forces. So perfluorocarbons are extremely nonpolar molecules. We already know polar molecules tend to not mix or not dissolve in nonpolar molecules. Well, perfluorocarbons are like a whole third category. They don't play well with others at all. So you can mix a polar compound, a nonpolar compound, and a perfluorocarbon, and you'll actually get 3 separate substances because they don't mix. Where is this advantageous? Well, in any setting where you don't want something to stick, whether it's oil or water. And the classic example is non-stick cookware. You probably know a lot of this as Teflon. Teflon is just the brand name for one particular perfluorocarbon. Another place where you don't want things to stick is to rainwear. So the famous substance Gore-Tex, which we think of as waterproofing for special types of rainwear, is actually another example of a perfluorocarbon. Now there's one other interesting quirk about perfluorocarbons, and that's that many of them are liquid, and they're liquids that are very, very good at dissolving oxygen, much better than water itself. In fact, they're so good at dissolving oxygen that creatures that normally can't breathe water can sometimes actually breathe perfluorocarbon liquid. If you've seen the movie The Abyss, the scene in The Abyss where they submerge a mouse into liquid and it continues breathing, that was a real scene. And the liquid was a perfluorocarbon liquid. Just a lot of carbon and fluorine, and that allows it to dissolve a lot of oxygen. Even though perfluorocarbon liquids do allow mammals to breathe in them, because they're so viscous, it's a lot of work for lungs that are normally used to breathing air. But there are some applications that people are hopeful these could be used for, especially things like premature babies who don't have fully developed lungs. To this day, people haven't been very successful implementing these, but the possibility is always there. Another very famous example of halogenated compounds is the broad class of molecules known as chlorofluorocarbons, or CFCs. CFCs have been in use for more than 100 years, and they were initially used in applications such as fire extinguishers. They can also be used as propellants, so when you need a substance to leave a bottle very quickly, such as a hairspray or maybe a pharmaceutical inhaler, you could use the CFC gases to accomplish that. Perhaps they were made most famous, though, by their use as refrigerants. That means that they were placed inside the condensing coils of refrigerating or freezing units in order to create a substance that could undergo changes in pressure and therefore cause changes in temperature. One of the most famous CFCs for this application is actually based on the relatively simple molecule methane. We know that methane consists of carbon connected to 4 hydrogen atoms. Well, if you replace the hydrogen with either chlorine or fluorine atoms, you have one of the most famous CFCs, which is freon. Depending on exactly how many chlorines and exactly how many fluorines, you have specific types of freon. So if you've ever heard the term Freon 11, Freon 12, or any other term that uses freon, you're actually referring to this relatively simple molecule. And it's a molecule that was made famous by the DuPont company. Now, what CFCs are probably most famous for today is their role in a process called ozone depletion. CFCs are gases, so when they're released either on purpose or by accident, they tend to rise up in our atmosphere. And CFCs, because of some of their chemical and physical properties, tend to not go away, meaning once they get into the upper levels of the atmosphere, they just float around there, usually for decades at a time. In particular, they tend to end up in a level of the atmosphere called the stratosphere, and that's where there are molecules called ozone. These ozone molecules act a little bit like a chemical sunscreen for the Earth because the ozone molecules absorb ultraviolet radiation coming from the sun and prevent it from getting down to the surface of the Earth. So ozone in the stratosphere is a good thing because it protects our Earth. It protects us. It means you have to wear less sunscreen when you go outside. But CFCs at that level of the atmosphere are very good at destroying ozone. And they're very good at destroying ozone in a process that actually causes them to regenerate. So what happens is you have a CFC molecule that chemically reacts with ozone, but then through a second process, the ozone can be reformed. So in the end, you end up with less ozone molecules, but the same number of CFCs. For this reason, CFCs were outlawed for most uses in the mid-1970s in most countries of the world. They're still allowed for use in very specific circumstances, but the nice thing is, because they were outlawed so long ago, our ozone layer, which had become rapidly depleted by the mid-1970s, has actually started to regenerate itself. But we've only seen that within about the last 10 years. So it was a very long process to wait for those CFCs to find their way out of that level of the atmosphere. The last example of halogenated compounds that I want to show you is a class of molecules called polyhalogenated aromatics. Many halogenated compounds are also aromatic molecules, meaning they contain the benzene ring or benzene-like structures. And generally, this has been a good thing because we find polyhalogenated aromatics in many facets of our modern lives. For example, polyhalogenated aromatics can be found in some pharmaceuticals that can allow us to overcome illness. They can also be found in materials that allow us to lead a safe and comfortable life. So while they have been central to the modern lives that we lead, we now know that they also have a dark side. That's because some polyhalogenated aromatics have been linked with some pretty significant health concerns. What type of concerns? Well, to be honest, ones that are a little bit scary. For instance, some polyhalogenated aromatics are either suspected or known to be carcinogens. That means they're linked with the occurrence of cancer. Other polyhalogenated aromatics can be linked to thyroid disorders or immune disorders in human beings. And because some of them can act like hormones, as well as for other reasons, they've also been linked to effects on reproduction, to everything from decreasing fertility to genetic disorders and birth defects. The other thing to consider about these polyhalogenated aromatics is that many of them are bioaccumulative. That's a term that means when they get into the human body, they tend to stay there for a while. So while you might only be exposed to very, very small amounts of the bad ones, they can stay in your body, and over time that effect starts to add up. I want to say one more thing before I show you some of these compounds. To keep things interesting, I've picked some particularly infamous compounds. And because of that, some of these compounds have controversial histories. After all, many of them are linked to some very scary health concerns. Because of the fact that this is a public lecture on the internet, I have to be pretty careful about what I say about these compounds. But you should feel free to explore them further because they're really interesting topics. In fact, each one of these could justify an entire lecture or even an entire class. The first infamous compound I want to show you is a compound called dichlorodiphenyl trichloroethane, much better known as DDT. DDT's structure includes 5 chlorine atoms, 2 of which are linked directly to 2 benzene rings. Now, DDT is probably most famously known as an insecticide. It was synthesized for the first time in 1874, but its use as an insecticide, something that kills insects, wasn't discovered until 1939. It was immediately put into use in Europe during World War II to kill off insects that could be carrying infectious disease, especially diseases like typhus. And for that reason, DDT was credited with saving tens of thousands of lives, both soldiers and civilians. After World War II, it was put into even more widespread use, eradicating insects like mosquitoes carrying malaria. So DDT actually started out with a very positive reputation, but the more widespread its use became, the more people became concerned about potential health and environmental concerns. And that came to a head really in 1962 when an author named Rachel Carson published a very famous book called Silent Spring. Silent Spring was an immediate bestseller, and it sort of jolted the public into awareness of some of the chemicals that were being put into the environment. Some people say it started the modern environmental movement. Because of this, people became aware that DDT was doing things like causing birds to have thinner eggshells. That was infamously linked with declining populations of California condors and peregrine falcons, as well as all of the concerns we've talked about that these compounds have for the human body. Because of this, DDT was banned for most uses in the United States in the mid-1970s. It's also banned in many countries around the world, but it's still employed in places where people believe that the risk of malaria is a greater threat than some of the other consequences. So that's DDT, a polyhalogenated aromatic. Another very infamous polyhalogenated aromatic are the compounds known as PCBs, polychlorinated biphenyls. These are compounds that have two benzene rings linked together and then some number of chlorine atoms on each benzene ring. PCBs have been around for quite a long time. They're very frequently used as an additive to many chemicals, including as plasticizers to manipulate the physical properties of different materials. They can also be used as electrical fluid in things like industrial transformers and capacitors. We've known that they were fairly toxic and had some real negative health consequences on humans since the 1930s. And for that reason, now PCBs are only allowed to be used in enclosed uses, ones where they're not exposed to the open air. But of course, when things are disposed of or when something ruptures or there's a spill, these can still get into the environment and they persist in the human body, amazingly so. So PCBs are another example of polyhalogenated aromatics. One other particularly infamous group of polyhalogenated aromatics are the compounds known as dioxins. Dioxins have a general structure of two benzene rings linked together through two ether bonds. The benzene rings then have some number of chlorine atoms substituting for hydrogens. Interestingly, we don't actually make dioxins for any specific reason. Rather, dioxins tend to result from certain industrial processes. In other words, they're just a byproduct. Some of the processes that can cause dioxins are processes such as bleaching. Right now, you're probably taking notes on a white sheet of paper. Well, in order to make that paper be white, it has to be bleached. And in the process of bleaching it, some dioxins were probably formed. Same thing with making paper towels or toilet paper. Also, a lot of manufacturing processes that involve chlorine tend to produce dioxins as a byproduct. And combustion itself, when we burn things, often can produce dioxins as a byproduct. In fact, dioxins have very, very negative health consequences, and this is one reason that eating charred meat can be bad for you. You're basically ingesting polyhalogenated aromatics, including potentially dioxins. Now, because dioxins are the byproduct of certain processes, they tend to end up in places where they really shouldn't be. As a result, there's some really famous cases out there of dioxin contamination. Just to name a couple, the use of the Agent Orange defoliant in Vietnam War is a really classic example. Agent Orange was a defoliating agent, just something that was sprayed to kill off plant life. And it was called Agent Orange only because it was delivered in large orange barrels. Well, it turns out those barrels and the Agent Orange in it was contaminated with dioxin. And this had horrifying health consequences, both for the people of Vietnam as well as the servicemen and women that worked with it. In fact, there are still court cases going through the systems in Vietnam and the United States about the health and environmental consequences of that dioxin contamination. Another very famous case of dioxin contamination happened at the Love Canal in the city of Niagara Falls, New York. While Love Canal sounds kind of intriguing, this was actually just a canal that was being built by a developer named William T. Love. When Love ran out of money, instead of having a canal, he basically just had a big hole in the ground. And the city of Niagara Falls, as well as local companies, started using it as a waste dump. The last company to use it was the Hooker Chemical Company, who buried about 20,000 gallons of toxic waste, sealed the dump, and buried it in soil. Unfortunately, despite knowing about the risks, the city of Niagara Falls decided to build homes and schools on that land. 30 years later, the truth came out, and they were forced to relocate thousands of people and destroy more than 800 homes, which were buried under the ground, and that land was permanently sealed off. And there's many other cases like that. Like I said, we don't really have time to go into them, but they're fascinating if you start to look them up on your own. One more thing I'd like to mention about polyhalogenated aromatics and dioxins specifically. Even though they definitely have a wide range of severe health effects, they have one classic symptom that's very obvious when you're exposed to them, and that's what's called chloracne. Chloracne gets its name because it's an acne-like condition that comes from the exposure to chlorine-containing compounds. Many polyhalogenated aromatics fall into that category. And it's not like normal acne. It's a really severe and potentially disfiguring type of acne that affects the face, the head, armpits, and groin. It was actually quite common in industrial workers in the late 1800s and the early 1900s. That's because they were working with many of these newer chemical compounds, yet we didn't have the health and safety regulations to protect them that we do today. In the modern era, it's unlikely that any American worker would be exposed to enough of these substances to get chloracne. However, in the event of an industrial accident, or when these chemicals are used in unregulated settings, then chloracne still exists. There's one other place, however, that we run into chloracne, and it's when dioxins and other polyhalogenated aromatic compounds are used maliciously to poison people. Now, this isn't the most common type of poisoning out there by far, but there are some very prolific examples of it, and I actually want to show you one. This is the poisoning case of Viktor Yushchenko. Mr. Yushchenko, who I believe was a pretty good-looking man, is the former president of the Ukraine. Back in 2004, he was running a fairly contentious political campaign, and he experienced dioxin poisoning. Now, we have to be careful here because, of course, he says his opponents poisoned him, and his opponents say he poisoned himself, and I'm not about to get into that argument. However, we do have a lot of evidence that suggests he did experience dioxin poisoning regardless of where it came from. As a result, he experienced chloracne. Now, I don't think it would be appropriate to show you one of the pictures of him from immediately after the poisoning because, quite frankly, they're really disturbing. Instead, I want to show you a picture from about a year later. You can see that this is not just acne. It is a real disfiguring condition, and imagine that industrial workers suffered with this for decades before we had appropriate safety measures in place. So chloracne, while maybe not as scary sounding as something like cancer or birth defects, is definitely a very severe condition that results from exposure to polyhalogenated aromatics such as dioxin. To finish up this lecture, I just want to briefly introduce one other functional group, and it's the functional group of thiols. Thiols are sulfur-containing compounds, and specifically their structure is virtually identical to an alcohol, except we replace the O from the alcohol with the S to make it a thiol. If you know anything about sulfur, you know that it has a very particular odor. And in fact, many thiols also have very pungent sulfur-like odors. The old name for thiols is to call them mercaptans. And in fact, this is still widely used throughout industry. So if you hear the word mercaptan or any version of mercaptan, it's probably a thiol-type compound. IUPAC naming for these compounds, however, is very simple. You simply take the name of whatever alkane-like molecule it's attached to, and you add the suffix thiol. So for alcohols, we saw that you could take a molecule like methane and change the ending to methanol. Well, with thiols, we'd take methane and we'd call it methane thiol. Let's try a couple examples. Take a second and name this molecule. This molecule has 4 carbons and the thiol group. We know that 4 carbons as an alkane would be butane, so we'll call this molecule butane thiol. I mentioned that many thiols have a particularly pungent odor. You're actually familiar with the odor of butane thiol if you've ever smelled natural gas. Butane thiol is added to natural gas so that we'd be able to detect a gas leak with our own noses. Without that, you wouldn't know if a gas leak was present because we can't smell methane. In fact, butane thiol is one of the substances the human nose is most sensitive to. It can be detected at extremely low levels, and that's one reason that gas companies choose to use it. Let's try one other one. Name this molecule. Okay, so this is still an alkane, but now it's a branched alkane, which means I have to decide how to number it and name its substituent. Giving the thiol group the priority, we see that there's also a methyl group located on the 3rd carbon. So to name this molecule, I would call it 3-methyl-butane thiol. 3-methyl-butane thiol also has a pretty nasty reputation when it comes to how your nose experiences it, because this is one of the main compounds that's responsible for the smell of a skunk spray. There's other compounds that are present as well that are also thiols. The only chemical reaction I want to mention with regard to thiols is oxidation. We're not going to go into this in a lot of detail, but I want you to be aware that this can happen because it's actually pretty important to understanding how certain compounds like proteins work. When 2 thiols are oxidized, it forms a connection between them called a disulfide or a sulfide bridge. So for example, if I have a thiol connected to an alkyl group and I place it next to another thiol with its own group, I can actually create a link between these 2 molecules. When I oxidize them using any general oxidizing agent, what happens is the 2 hydrogens in question are going to be removed. In their place, we'll create a new single bond. The product of this reaction is essentially the 2 thiols linked together through that disulfide or sulfide bridge. So whether the R groups were methyl groups or whether they were some very large and complex protein structure, it creates a linkage. So many proteins actually contain these disulfide bonds between 2 thiol groups, and some of these proteins are ones you're probably familiar with. For example, keratin. Keratin is a protein that's in our hair as well as in our nails. That structure of keratin partly comes from this disulfide bond, the connection between 2 sulfur atoms. One of the reasons your nails are as hard as they are comes from that actual link between the sulfurs. And in fact, the texture of your hair is partly due to these disulfide bonds. When someone goes to get their hair either permed or relaxed, you're actually using either an oxidizing or reducing agent to break and relink those bonds. It's not just humans that have keratin. Birds also have a lot of keratin as well, and that's because the structure of their feathers comes from the keratin protein. In fact, one of the reasons that you may associate the smell of sulfur with eggs is that eggs have to contain a lot of keratin that will eventually go on to become the feathers of that bird. Other proteins that contain these disulfide links are proteins like collagen and insulin. I want to mention one other place that these disulfides play an interesting role, and that's in rubber. We think of rubber as a bouncy, stretchy substance. There's actually a lot of different substances that we use and call rubber in our modern lives. Some of it's synthetic and some of it's derived from natural sources. But originally, rubber was derived from one particular tree. And it wasn't as bouncy and flexible as the rubber that we think of today until chemists realized that by heating the raw material in the presence of sulfur, they could create this much more flexible material, partly due to the way the thiol and disulfide bonds formed. This process was called vulcanization, and in fact we still use vulcanization today. It's one of the reasons that we associate burning rubber with such a bad smell. It's actually a thiol-like compound. That's where we'll finish this lecture. I hope it was as fun for you as it was for me. In our next unit, we'll start to look at some new functional groups.